I'm talking about Turbopack and about how DX matters for us. And my name is Tobias Koppers. I'm founded Webpack like 11 years ago and maintained it for a long time. And then I joined Vercel and worked on Next.js, which is like a framework for developing web applications. And since like 1 year, I'm working on Turbopack, which basically means building a kind of a successor for Webpack, a new version which is better. And today I want to talk about like a few motivations why I did that or why we did that, and what's our approach in this space, and what challenges we occur with JavaScript and Rust, and yeah, and some kind of new ideas we had in mind and what the future will be about. So we start with the like motivation about this project. So like we worked, also while I'm working on Next.js, we trying to optimize Next.js to be more DX focused, improve the developer experience of it, like performance and that stuff. And we hit a lot of challenges with that. Like one of the main challenges was performance. So basically we spent like 1 year about like optimizing Webpack with Next.js, and like eventually we hit some limits where we can't really optimize Webpack further, and yeah, we can't really improve the performance more, especially when like it was fine for smaller mid-range applications, but especially when grow with larger applications, like HMR gets really gets slower, and our goal was like at least below 1 second, and yeah, we can it can get up to like 10 seconds for a large application. That was not acceptable for us. Reason for that was mostly bookkeeping and restoring from cache overhead, and which kind of goes deep into the architecture of Webpack. So this was a problem. And similar problem occurred with like production builds, where like builds get slow when applications grow. Like that's kind of bad, and there are some problems with JavaScript as language. Like JavaScript is single-threaded, so it's like hard to use multi-threaded, use all for your cores to actually build stuff. And the JavaScript is not really that well suited for building high-performance applications. Like there's some implicit overhead of writing JavaScript applications. You can't go really deep into low-level optimizations of performance. Yeah, we tried to replace some parts of Webpack and Next.js with native code. Like we replaced the JavaScript parser with SWC, which is a Rust-based parser, which works well, but only because like the API surface between parsing a file and transforming a file and getting it to Webpack was only like passing a string back and forth. But that works well. But if you want to replace deeper parts of Webpack, you basically have to serialize larger object structures, and that the overhead of this serialization cost between the languages was too high. And we tried it, but it just was too higher than parsing it in JavaScript. And so it was like not really possible to partially replace stuff with native stuff. It was possible for some for some parts, but not for like the bigger things. Another challenge was like in Next.js, we basically don't do like only a client-side bundle. We do client-side code, we have server-side code, we have different kind of server-side code. We have like middleware code which runs on edge workers. We have code that runs on AWS Lambdas. We have code that's for server-side rendering. We have code that renders server components. So different kind of environments we want to run a code in your application. And one problem was like we needed multiple Webpack compilers. We need one compiler for client-side code, one for server-side code, one for server actions. Like all the different kind of environments needed different compilers because Webpack was not able to handle this code, these different environments in one compiler easily. And this resulted in that there's a lot of communication or orchestration needed between these compilers. Like we have to make sure that server compiler executes before client compiler, and then this causes this to rerun, and it's a lot of orchestration work, and that has an overhead, and especially is a source of errors. Like there are some race conditions we had where like it's not correct, running in the correct order, and everything runs in parallel and whatever. Resulted in slowness and resulted in errors, and it's a source of pain for internal development. It actually slowed down like the development a lot because you have to take care and test all this kind of weird interactions between different compilers. It also made it different or harder to implement newer patterns where we want to have even more transitions between environments. Like we added server actions, which is like some kind of RPC call from client-side code. You have your server component calling into client-side code calling into server actions again. So you have more transitions in the graph, and that really makes it difficult, like to embrace or innovate on these kind of new patterns you want to have in web applications. Basically making it kind of a technical limit where we can innovate or like improve our kind of application development flow with Webpack. On Webpack side, there's also a larger DX challenge, which is like the configuration. It was really overwhelming. It's like there are a lot of configuration options, and users often write it once, don't understand it, and like it's like staying there, and yeah, there's kind of weird source of errors because you have some configuration added like 10 years ago or 2 years ago, and then like they like causing errors because of this configuration added configuration options copied from the internet 2 years ago or something like that. There's also a problem with like it has two really low-level defaults. So it's like Webpack is more low-level tool, so you have to add like your stuff on top of it, which caused also that people have a lot of configuration, and that's also kind of problem because you actually want it like it was fine like when Webpack was created like 10 years or 5 years ago, but nowadays like the web ecosystem like maybe settled down a little bit on what other kind of common tools like TypeScript or like SAS or that kind of tools are more standardized, and you actually expect it to be working out of the box instead of like you have to add them on top of something. So that's nowadays it's my kind of a problem in Webpack configuration that you have to add this kind of defaults which should be out of the box. There was also some changes regarding Next.js. So Next.js also had this kind of special mode for lambdas. So basically, in lambdas, it try to you can just copy like all your code into a lambda and execute it, but then you get this really big code base with all of your node modules, and that's kind of not what you want to. So Next.js had this mode that it only it follows the graph of your function and only copies like that files of node modules that are needed for the lambda, which kind of makes sense, but also it couldn't use Webpack for that because Webpack is basically a bundler. It bundles code together, and in these cases you don't. So in many cases, Node.js executed code can't be bundled because of native code or kind of weird patterns in these kind of things that basically not aware of being bundled in contrast to client-side code. In this case, like Next.js couldn't use Webpack and basically implemented its own tool. It had an additional tool which just follows the graph and copies over the code to the lambda, which is a source of inconsistency because like Webpack bundle code and this kind of NFT is called the tool code was resolved and traced in different ways, and that causes inconsistencies, which you want to avoid. So all these changes led to the idea of like writing a new bundler, writing a new tool to take care of like these challenges, making a bit better improvement of that. But it's also a really huge investment. It's like maybe 2 years, like what you need for building such a tool. And is it really worth for just a little bit of DX improvements? And we think it is worth it, and we also can make sure that it's really worth it by like having some kind of additional ideas that make it really beneficial from writing a new tool. Like we could enable a few new features, like make it easier to like make better optimizations, make smarter bundling techniques which we can use. It also should enable like internal speed up of the development, so we can implement features faster in Next.js, implement new ideas, new workflows in an easier way. And the basic idea of that tool is that we want to make a tool that works for the next 10 years, similar to Webpack, which was exactly 10 years old when we started with that. And 10 years is pretty long in web development, so if you take a look at what happens, like the last 10 years, it was like small applications with like 100 of files of JavaScript, which it's not really lot stuff, and nowadays we have 10,000s of modules in JavaScript applications, which like even more if you multiply it by server client code and that kind of stuff. So it's really growth, and if you like extrapolate that for the next 10 years, we could expect like maybe millions of modules and code, a lot of code in web applications. So we really want to create something that is working for the next 10 years. Maybe not in the current state, but like at least it has the potential to be easily adapted to like the growing number of modules, the requirements of the next 10 years. So we want to make a really good new architecture, good architecture that is suited for that, and especially performance-wise, which was, I think, the main challenge in adapting Webpack over the last 10 years. So in the end, we really want to build the successor to Webpack, which like Webpack 10 years, Turbopack 10 years, so that's like kind of our ideas. Yeah. So that's why we came up with some kind of goals for this kind of project. So one goal was like we want to make it like general purpose. So we want to start with Next.js as first customer, but in the end, the goal is to make it general purpose for all frameworks or for like similar Webpack, which is also general purpose and usable for everyone. And in this kind of sense, we also make it as similar as Webpack, really flexible. Maybe not that much, but at least a lot of flexibility in Turbopack also. And we also want to make some improvements to the graph building. So we want to make it more flexible in the sense of what can be in the graph. This comes back to the patterns where we have client-server code interleaved, and the graph should be flexible enough to cover this case. So it shouldn't be needed to use different compilers just for different environments. It should be in one graph, and this also enables a lot of more potential. Like you can optimize between this kind of environments. Like the client is using this export from the server, and then you can do tree shaking between graphs and that kind of stuff. It enables new kind of features and also makes development much easier because you don't need the orchestration between different compilers, and it's just one graph that covers all of it. And the biggest goals were regarding performance, because that's where Webpack suffered the most. And our approach, or our goal here was like, we want to focus really down on incremental builds, so making incremental builds as fast as possible. And we basically had this like kind of goal in the mind, that incremental builds should be independent of application size. So basically, if you do like an incremental build, maybe from file change or like also in production, it should only like scale regarding to the size of the change, like maybe what affected of the application, but not of the whole application. So if you have millions of modules and only change one of these, it should be as fast as like changing one module in application of hundreds of modules. At least that's the goal. It's like really hard to do. Yeah, basically with this incremental idea, we also had this idea of being incremental first. So like if we have a bundler where incremental builds are really fast, we also want to make sure that like every build is incremental, or at least most of the builds are incremental. So that's why we invested in like ideas of like persistent caching. So you don't have, if you restart your server, it should keep the cache, and also remote caching, and also for production builds, using persistent caching or remote caching and that kind of stuff. It's also a little bit difficult to design it in a way, a little bit interesting to design it in a way that like every piece of the bundler is really incremental. So everything, even if you like do an optimization, figure out the modules and that kind of stuff, like every operation in the kind of process should be incrementally aware and be incrementally cached and incrementally computed. Another idea or goal was to make it also lazy by default. In the case where you don't have a cache, maybe you're starting your dev server for the first time at all, and then we should also be lazy. So if you only request like one page or one JavaScript file or one bundle, then we only want to compute that kind of file or this kind of page and don't do anything else in the application. So basically lazy by default, and everything should be lazy, and we only really build what we actually need. Yeah, one obvious goal is is also use multi-threading. Like if we JavaScript was single-threaded, that was a problem, and nowadays like every computer has like tons of CPUs, and we want to really leverage all of this power. So that's where the story begins. We basically started with a kind of prototype of this kind of a kind of new architecture, which is basically the incremental first design, and it was really working really well. It was really super incrementally fast, and we were really surprised that it's working that well. And from that prototype off, we basically split it off like as a new team from the Next.js team, and like to build like a new bundler, Turbopack. And we built it in 3 layers, which you see here. So one layer was like we built everything on top of Rust, mainly because SWC is built in Rust, and we want to really integrate well with it, and without having a serialization cost between languages. But also because Rust is a great language to use multiple CPUs, and it's also really type safe and good to develop a large application. And performance is also really great in Rust, and easy to write performant code. On top of Rust, we built this engine called Turbo Engine, which is like the incremental computation engine, which I tell more about later. It's basically an incremental computation engine, which takes care of all this incremental building stuff. And on top of this engine, we built Turbopack, which is like the bundler itself, a general purpose bundler. And on top of Turbopack, we built like a Next.js integration for Turbopack, which is then basically using Turbopack instead of Webpack. Yeah. So our approach regarding the goals for like a general purpose bundler was this kind of splitting between layers. Like we also split like Turbopack code into a different repository than the Next.js code to make it really separated and to force us to make Turbopack general purpose and not trying to avoid leaking Next.js specifics into Turbopack to make it at least eventually general purpose and public and reusable. This also leads to it forces also us to make it kind of plug-in system because Next need to use a plug-in system to integrate with or bring Next.js specific stuff into Turbopack. And our goal for that, and also for like a general purpose and flexible tool, was to make a plug-in system that is split into 2 parts. Like you can, eventually you should be able to write plugins in Rust or in JavaScript. Rust to make it able to like write high performance code if you really care. If it's necessary for your plugin, which probably rarely is, but if it's necessary, you should be able to write a Rust plugin which is in really performant integrated into Turbopack. And for the common case, I think you should be able to write JavaScript plugins, which is a lot easier to write and also more approachable for the average web developer than you write plugins in JavaScript, and should have the similar power, maybe not so low level, but at least really similar power to Rust plugins, but it's easier to write and should also work. We also have some kind of currently internal configuration, which is allows you to configure Turbopack in a way. An example, Next.js is configuring is using a configuration to control Turbopack. It's currently internal, but we want to make it public. But I think we should spend more time in making a good public API, public configuration before making it public. So I think we need some time to think about it too, because once you make it public, it's harder to change, and people don't want you to change it. So once we figure it out, we make it a public configuration, and then it should be usable similar to Webpack. So regarding the graph, we wanted to make a really flexible graph, and so to achieve that, we got away from this kind of idea of there's a compiler with some configuration. So we basically avoided global configuration at all. So there's only local configuration, which means you have an entry point, and then you attach some configuration for that, and then the configuration is basically attached to the graph itself, and it follows the graph. And once you transition between environments, like from server to client, you can change the configuration at that point or use different configuration, and then this is basically attached to the graph. So basically not there's a compiler with global information, but instead there's a graph, and at every node you have some kind of configuration applied to that and can change it anytime and transition between different configurations and different environments, and that makes it really flexible to use this kind of graph. We also wanted to do something similar with, like, if you have some kind of config file, like maybe tsconfig or some kind of Turbopack config which doesn't exist yet, and it should also be able to apply that locally. So like, if you have a file, basically, instead of having like a global Turbopack config.js or whatever, it basically will pull the configuration at the folder level. So any file, you can put it like anywhere in your folder, in your monorepo, and then it only applies to like that subfolder and that kind of stuff. So everything's local configuration by default, and it should make it more flexible in how things are configured, and more flexible even to like also to use different configurations at different parts of the application. Also in regard of monorepos, where you often have different packages split between teams, and they might have different configuration choices, and that should also enable that kind of thing. The most difficult thing was like performance approach. And we want to have this incremental kind of thing. So we built this new architecture called Turbo Engine. And it's basically built on top of reactive programming concepts. So reactive programming is something like you have some kind of function, and then it basically automatically tracks if you read some value that this depends on that value, and then if this value changes, then it will recompute that function. So basically it builds a graph out of your application, the dependency graph, and then it can follow that and use this graph to like recompute stuff and basically react on changes on that stuff. It's also memorized by default, so every function you execute is only executed once and basically cached by default. So that makes it easy to cache. And this reactive programming approach with dependency tracking between values and functions also make it able to like give you cache invalidation by default. So by tracking all the values, you can easily, if something changed, follow the graph, invalidate the right caches, and easily granularly cache stuff instead of having like this broader range caching that is in Webpack. So I had a kind of demo for that, not a demo, but a kind of graph for that. Like, you can imagine this is a compilation. It's probably larger, but it's basically a bunch of, like, it's only like for a reference, not really, it doesn't really matter what the content is, but it's like you have this graph of different functions calling each other and having dependencies between each other. And maybe that's initial compilation, you compile every function, and while doing that, you track the dependency between the function. Like, if you think about like, like parsing ECMAScript, so like if you want to get the references of a module, then you have to execute parse TypeScript function, and then you also depend on the result of that. So like, in this case, like, and parsing TypeScript depends on reading the file. So in this case, you have the dependency graph between all these function calls, and also maybe multiple of that. And the funny thing that happens is, in the case of a file change, like, let's assume that this read file changes, and you want to do an incremental compilation. You start by everything is cached, so it's just sitting around, memorized, nothing to do. But once the file changed, it will basically re-execute this kind of function, and then you propagate the change through the graph by following the dependency graphs. And in the end, the graph eventually converges to like a new state where everything is updated. And you can also do some funny things like this, where like you re-execute this function, but you see the result has not changed by comparing to the old value. And in this case, you don't have to propagate the change to the dependent task. So this is like the eventually consistent thing of propagating the whole system to a new state. And the good thing on that is you basically don't have to touch any of the gray nodes. It can be like millions of that, but you like, if the file changed, you only follow the few edges in the graph, and you change, like applying the change to the graph basically only depends on the size of the change or of the affected graph and not of the whole graph. And that's the whole idea about making incremental builds independent of application size. So back to the slide. Maybe it's not that easy, but you also have to keep, while writing code in the system, you also have to keep in mind that this is incremental, so it would be a mistake to use one function to walk the whole graph, then you will be dependent on application size again. So you need to be a little bit aware of that your function might be re-executed and that you keep your functions small and not walking the whole graph or walking a lot of stuff. You also have to keep persistency in mind. So as you want to be persistent and remote cacheable, you must make sure that your results are serializable, and if they are not remotely cached. So maybe it's possible, and we do it for a bunch of things like the AST. We don't cache that persistently, but yeah, you have to be aware of that and make sure that you keep that in mind. Another thing we do is a lot of benchmarking infrastructure, profiling infrastructure to really make sure that we stay fast and our builds are really, our incremental builds are not dependent on the size. We also want to expose this kind of tracing benchmarking infrastructure to the user. So we want to give the user more insight how the build behaves. So that historically you don't have a lot of tools to really see what's slow in your application, and we really want to make it able to see this kind of graph and see where the time is spent and make a useful visualization of this kind of graph and the timing spent in each function and that kind of stuff. There's also some kind of changes or approaches regarding performance in Turbopack itself. So the previous thing was mostly Turbo Engine, now it's Turbopack, and here it's mostly the lazy by default idea. So we just basically want to avoid having a module graph in our system, or having a structure that represents a module graph, because a module graph would be scaling by application size. So updating that would be also depending on application size. So we instead of having this large graph, we instead use an implicit graph approach where you have nodes and you reading or getting the children of one node is a function you can execute, and as every function is memorized and incremental, it also benefits from Turbo Engine, where you basically walking the graph just computes the graph, and this way it's similar to an implicit graph and not having one structure for the whole graph. It's also the kind of tricky thing is we basically want to avoid global information. Any kind of global information would require to walk the graph, or the whole graph, and that would break the lazy thing, because walking the whole graph need to evaluate or compute the whole graph, and that's not lazy. We tried, or we avoided any kind of global information in development builds. So you can't really, global information could be something like how often is the module imported, or which are the parents of one module. And that kind of information, we can't really get that. So we need to restructure some of the algorithms to basically avoid this information and can just do stuff without this information. This requires some refactoring, but in the end, we had this, and it has some trade-offs where you made things worse because you don't have this information about other things in the graph. You have to rely on some heuristics to deduplicate between stuff. But in the end, it seemed to work really well, and that's kind of the challenges here. Also, a similar thing to benchmarking and profiling is really important to ensure that everything is working well. So that was the approach. Now the challenges. One of the biggest challenges I think was Rust. basically most of the team members were new in writing Rust code at all, including me. So I never wrote Rust code before, so I basically learned Rust while writing this project. And it can be hard. It's like a new language, different paradigms, and especially with Turbo Engine, which is this incremental way, it's like a different way of writing Rust code. It's like similar to a different language on top of Rust. And yeah, it's like a little bit hard to learn, and it slowed down maybe like new members joining on the team. Yeah, but there was also some other challenges in Rust, like the development process. The Rust is really slow to compile, especially when coming from the JavaScript world, where everything is like interpreted, and like you start the application, it doesn't need any pre-compilation step, or maybe a minimal pre-compilation step. So that's really slowing down, at least me in development. If you have to wait a bunch of seconds or maybe multiple minutes to Rust compile your application just to start it, that's really annoying. But on the other hand, it makes it easier to review pull requests because Rust is really strongly type checked. So if your coworker submits a pull request, you can be sure that every type is correct in this. If the CI is passing, of course, is correct in this pull request. You can basically skim over like all the import statement, all the type adjustments or whatever, and you can concentrate on the logic changed in the pull request, and it makes it much easier to review pull requests compared to JavaScript, where you had to review every type and every, like, is this really safe, type safe, like, oh yeah, basically it's easier to review. Especially as Rust is more verbose in writing, so it's like good that it's easier to review. Yeah, the build process is also a problem for the production builds in Rust. So like there was a while where it took like 1.5 hours to compile a new version of Next.js because like the Rust compilation step took so long. Yeah, that's annoying and really problematic. And the problem was like it's running on GitHub Actions, and that's not the fastest one. So eventually we replaced the CCI with faster machines, and then it was faster. But this was really annoying for a while. Yeah, it also comes down to the deployment process. Yeah, basically in JavaScript world, you just write in JavaScript code, publish an NPM package, and it's just working everywhere. But in the native world, you basically have to compile binaries for every platform you want to support, and as it's open source project, you probably you want to support every platform. So it's like I think it's like 6 different platforms you want to compile every. Like the build process is not the easiest one. You have to compile on Windows, on Mac, on Linux, and on different platforms, and with different VMs and Docker images. It's like super complicated and yeah, annoying. And it also results in larger binaries. Like I think it's currently 100 megabytes about like a Turbopack binary. It's not super optimized yet, but yeah, it's much larger from download perspective compared to like JavaScript code, which is a lot smaller, and at least compressed better. Yeah. So yeah, that's problematic, and it's also like is problematic, especially problematic if you want to write okay, we handled that kind of process. That's fine, it's working. But if you want to users be able to publish Rust native plugins for Turbopack, they also have to go through the whole process. Like they have to build it for different platforms and deploy it in a similar way as we do. And yeah, that could be a lot of pain for the plugin developers. There is a possibility to use WebAssembly-based plugins, but it's make it easier to like have this build deployment process. But it's also slower, and that could be a problem. And there are different challenges regarding some stuff in Rust is not compilable to WebAssembly and that kind of thing. Yeah, so it's a trade-off, and yeah, and especially if you want to write a Rust plugin, you probably care about performance, or the JavaScript plugin is not enough for you, so it's probably not like good enough to write a WebAssembly plugin, which would be slower. Yeah, that's why JavaScript plugins is much easier, and is also really important for us, because it's easier to write, easier to build, easier to deploy, yeah, but there are other challenges regarding cache invalidation. Example, like in Rust, you have like really, due to the type system, you have really tight control. You can't easily import global state, and you can't easily import from module scope variables and that kind of stuff. In the JavaScript, you can just like access global state, global this everywhere, and yeah, leak state, and yeah, basically breaks the cache invalidation in weird ways if you don't be careful, which is much harder in Rust. Yeah, so it's a little bit tricky. So technically, config files are also kind of JavaScript plugins. Like if you have maybe not a TS config, but like anything .js config, a config.js file, then it's basically executed in Node.js. It can import other files, and it's basically similar to a JavaScript plugin. And the challenge here is like we want to make cache invalidation working for that, or caching working for that, and incremental builds working for that. So we have to really, if this file has changed, we have to re-execute it. But not only if this file has changed, but also like if the config file is importing another file, and if this is importing another file, and this transitively imported file is changed, then we have to invalidate the cache of the config file. So we really have to follow the graph of config files similar to what the bundler is doing. So that's also cool that we can do that. Yeah, another change was this turbo engine design. So we basically built this cool graph of all the tasks in the application, and yeah, this also leads to problems because this graph can be really large. It's like millions of tasks in a graph, and then you have like even more dependency edges between them, and that leads to performance problems because you have to do graph operations in like a graph of millions of nodes, and that, yeah, it's like not the easiest. You have to be really careful in doing that without like creating artificial performance problems due to the way the graph is built and that kind of stuff. It also has a problem of memory footprint. Like the graph of millions of nodes to store has a cost, and yeah, that's a problem. And we're working on reducing that, but currently it's like a big problem in Turbopack, and yeah, it probably will be tackled by persistence, because then we can like put some of the graph into this file system, basically swapping out the graph, and that could reduce the memory footprint. Yeah. Also, the kind of memorization system, like memorizing every function, is also like contributing to the memory footprint, like storing every value in the application is obviously, it's basically a memory leak in the kind of thing. So we also working, or we have a system which is a kind of garbage collection system, so you're throwing away values that were computed before. And that kind of works well because like in our system where like you execute a function that's memorized by default, and then this is kind of, so that's a system, you can just throw away any task any time. And then like the next time it's accessed, it's just recomputed. It only has a performance cost, but you can throw away everything if you want to. So it, in the end, if everything is working as we plan it to be, it will just like have a memory limit, and then it will throw away everything that's below the memory limit, and we keep below the memory limit. Or maybe not throwing away, but by maybe serializing to dist, hopefully, or throwing it away. Yeah. Another challenge with Turbo Engine was like consistency. So like I said it before with the graph, you have this like file chains bubbling through the graph, eventually propagating to like an updated state of the graph. But this eventually propagating is sometimes a problem, because like if a request comes in, you don't want to like maybe respond with stale data, maybe it had propagated to the updated state and then respond with good data. You always want to respond with updated data. So you never want to like respond with stale data on a request. That would be weird. And yeah, so we have to tackle this problem by offering also like, instead of only having this eventual consistent read kind of thing, we also want to, at some points of the graph, like requests, we want to like respond with some strongly consistent readed values. So like we want to like wait for the graph to be propagated until this point and then respond with the value. And that's also a little bit difficult because you don't want to walk the whole graph because then it's dependent on application size. That's not what we want. So we want to come up with a clever optimization technique or structure to like wait for the graph to be propagated until this point and then respond with it. So like strongly consistent reads. Yeah. But on the other side, we also want to have some kind of like inactive, active kind of state of nodes. Like if you like have this request coming in, responding with something, and like it's done, and then the file is changed, we don't want to propagate the value to the request because that's unnecessary. The request is already handled, so we don't want to like eagerly propagate the values to the graph. So we also have like a state of active nets or inactive and active for nodes. Like some of them are active because you're watching them over WebSocket. Some of them are inactive because you, like in the past, you like served the request with that, and you currently no requests coming in. And this also avoids like overcomputing. So like we don't want to overcompute inactive values. We only want to propagate the graph until the graph is as long as the graph is active, and don't propagate into inactive stuff. Yeah, and that also basically contributes to the problem of responding with stale data, where the request comes in and only then the graph is flagged as active because then the request is handled and it starts propagating at this point. Yeah, yeah, it's clever. I think we have an approach to handle that, but I think it's not the best one. It's working, but there's also some performance problems with that. So I think we want to rethink that. Yeah, but it's fine for now. So new ideas. So in the past we do linting, but linting is often only on file level or maybe like in ports or stuff. But I think we can use like the module graph for linting, or we can use all the graphs for linting stuff. Like maybe in the module graph we could something like files from that folder must not be imported from that folder, like to enforce architecturally designs and basically make clever, smarter lints based on your architecture of the application. Also to provide like safety guarantees, like this is security sensitive code and it must not be imported from client-side code or something like that. Yeah, so we want to provide more linting. Another problem especially regarding warnings, is that users are often overwhelmed with warnings. Like sometimes there are none, but often there are like millions of them, and then the users don't read them, like skip over them, and it's not really useful. So we want to like have some better like visualization for warnings, maybe in kind of UI instead of printing everything from the console. And often users are only interested in like new warnings that like occurred while they're doing changes. Like, yeah, they often don't care about like the millions of existing warnings. So we really want to find better visualizations for that. We also have some new ideas regarding a build introspection. So like I teased it before, like we really want you to like look into these graphs and like inspect them, and you can really find valuable information from that. Like in the module graph, if you're like this small module imports like millions of other modules, you might want to look into that. Or in the output graph is if you lazy loading like or eagerly loading like tens of megabytes of code, then that might not be good. And in the build graph, if like 90% of the build time is spent in like compiling this third-party package, then you might want to do something about that. So the graph contains really useful information, and introspection might be really useful for that. But it's often difficult for users to like, even if they see the graph, to like understand what's the right action to do, like what can I do for that, and what should I do? And I think we need a really better view of you have to take, or you should take this action, or this is a proposed action to do that, or to fix that. And yeah. And this kind of introspection is especially valuable in like if you have a pull request based approach where you can actually like show like the diff of the pull request as introspection of the graph, and that's really useful. We also want to give you more control over the build. Like sometimes it happens that you have errors or problems that only appears in a production only, like in a production build, and not in your dev server build. And yeah, it's really hard to debug this kind of problem because like you have this minified code and no source maps, and you really can't really debug this stuff without reading gibberish code, and that's hard to do. So I really imagine a world where you have the dev server and have a slider where you can slide between dev and production build and enable optimizations based on that, and then you can just debug your production version of your web application in your dev server with some optimization turned on. Basically, move the slider until your problem disappears, and then use you basically can get a version where you have to just see your problem, but still have a lot of possibility to debug. There's also more possibility of optimizations. I talked before that. That's currently basically modules are the lowest level of optimization. We can optimize some exports of these modules, but it's basically the lowest unit of optimization. But we can do better. We can split up modules into statements and declarations and use this as optimization. Basically build a much larger graph of statements and declarations and optimize between them. And also some of the optimizations are limited by the specification. So in example, if you import some code, it has to be executed, or side effects in this code have to be executed. So there are some possibilities to offer opt-outs for package authors, like setX false is one option of that. And we could add more for lazy evaluation, and that should be able to offer more optimizations. So last slide. There's also some optimizations opportunities in different environments. Like currently, we often focused on web performance optimization, web development, web on the client-side code, but there's potential for special optimizations for Lambda code and for code in edge workers. And Lambdas, in example, you know that Node.js execute code, and it's you can do special optimizations for that. On edge workers, it's a single bundle, and So thanks for listening to that. It's really long. I hope you learned something new, and thanks for coming.